I'm ZAINAB, and I'm going to be speaking to you on the challenges of concurrent systems. You can find the slides, by the way, online over there. So I hope everyone can see. It's a very big screen, but if not, you can go there. You'll see the exact same copy. Okay, let's set the scene. I want you to imagine that you're a junior developer. We all were once. You work in a small team in a pretty small company, and it's not doing so well. It doesn't have very many customers. Now, one morning, your manager comes up to you and gives you a task. I need you to design a web service, she says. Well, what sort? You ask. It's a very simple one, just a counting service. It just needs one endpoint, and it's only for demo purposes. We're going to give it to our salesperson, and he's just going to show it to a few customers. Well, that sounds fine. It's just a demo. In fact, it's the perfect task for you because you've never written a web service before, never from scratch anyway. You code it quickly, and things seem to go well. You get some feedback, there are a few bugs, but that's fine, you can fix them. The salesperson, after all, he only works on Fridays, so in fact you can just take the system down any other time and only whip it up then. Well, things go well, and you add more and more features, it gets a little bit more complicated. And then one day, something amazing happens. Your company makes a sale. Congratulations, your manager says. We've finally sold this system, and we have some customers. In fact, we have loads of them. Your sales team is having a great day. The whole company is celebrating. Except you, because you're now looking at the contract. You're now looking at how many customers you're going to have, thousands of users at any time, and also how often it needs to be up, 100% of the time. So even when you roll out new versions, you can't take your system down. So while everybody else is out celebrating, you're inside and you're scratching your head. And you're wondering how on earth you're going to achieve this. Now, scaling a system is hard. And it's not hard because systems at scale are hard. Systems at scale are actually necessarily simple. Scaling a system is hard purely because you haven't done it before. You don't have the experience in scaling systems, in designing large-scale ones. And so when it comes to writing that first system from scratch, you don't design it to be scaled. Now, the challenge of scale is the challenge of concurrency. You don't always need to care about it. Let's say that you're writing an admin script for yourself or for your team. It just runs once every so often. You don't really need to worry about concurrency at all. Let's say that you're writing a system for some internal users. Maybe there are only 10 of them and they don't use it too often. You do need to think about concurrency a little bit, but not too much. But for a lot of systems, handling concurrency is vital. If not when they're small at the beginning, then certainly when they're successful. Well, concurrency is challenging, but it doesn't have to be. I'm ZAINAB. I'm a functional programmer, and I'm also a trainer and mentor. And I train people to build concurrent systems. I really love functional languages. I love lots of them. But in particular, I like Scala. And does anyone here, by the way, use Scala? Oh, a few. OK. I'm really glad to see that. You may not know this, but I am your community rep. So what that means is that if you have any suggestions of improvement, you can come and speak to me, and I can see how we can get that done. I also run the local meetup, so if you ever want to come along, I organise the London Scala Users Group. We're a really friendly bunch. It's a small crowd, and we meet up once a month, and we talk about systems like these. I'm also a Scala ambassador. I don't know if anyone can see that little logo. down on the other side of my laptop. It's a great honor to be one. I was nominated one. And that means that anyone can come and speak to me, and I'll try and point you to the best resources to start learning Scala. I'm also really passionate about open source. I really like contributing to open source libraries and also maintaining a few. And in particular, I like the type-level ecosystem. And that's one that I'll show you a little bit about. But that said, you don't need to know anything about Scala for this talk, and I'm honestly not trying to indoctrinate you. We're not here to learn Scala. We are here to learn how to write concurrent systems. And so you'll see how Scala might help, but it's really about the different tools that the ecosystem gives you in order to enable that. So here's our agenda. First of all, we're going to look at reasoning. We're going to look at how we think about concurrent systems on paper and how we solve concurrency bugs. After that, we're going to take a look at the systems beneath our application, everything from our application to the actual processor, and we're going to try and understand just a little bit about how it runs and about how concurrency actually works. And then finally, we'll take a little look at asynchronous programming, which is a new model of thinking about concurrency. So first of all, let's take a look at reasoning. We're going to explore what concurrency is and how we should think about it. To demonstrate that, I'm going to give you a concrete example, and actually a physical one. So at the moment, I'm doing several things at once. I'm walking around and I'm speaking to you. And I also have a glass of water here, and I can drink some, and I shall. But I can't drink and speak at the same time, right? That wouldn't work. However, I can still do many things at the same time. At the end of this talk, I might have drained my glass. And so I can do things concurrently. Concurrently is a very hand-wavy way of saying, or rather, at the same time is a very hand-wavy way of saying concurrency. We're going to describe it in more detail in a second. So let's think about concurrency then in our web service. I want you to imagine that this is the web service that you wrote. This is the endpoint for counting. It's one endpoint. It's called increase. And you give it a number, in this case 2. And what it does is that it keeps some internal count. It prints the count before and the count after. So let's say that the count before was 1. And you give it an increment of 2. It should print count before is 1 and count after is 3. But there's a slight problem with this system. Suppose that you make these 2 requests and you do them at the same time, really, really fast to your eyes. You say increment 2 and increment 4. And later on, you take a look at the logs of your system, and this is what you see. The count before is 1, but the count after, at the very end, is 5. And that's strange, right? I mean, 1 plus 2 plus 4, I can do basic arithmetic. That's not what I get. Now, the even stranger thing is that when you go and inspect your service, you actually see that the count isn't 5. The count is 3. So this is an example of a concurrency bug. It's actually a very simple bug. Now here's the code for this service, and the bug is in there. But I don't want you to identify it at this moment. Some of you, I'm sure, already have. What we're here to do is take a look at the techniques we use to actually identify the bug. All right, so when we talk about concurrency, we're talking about doing multiple things at once, or rather at the same time. Now, in this case, I want us to consider just 2 calls here, the call to get and the call to set. So get gets the value of our count, and set sets the value of our count to something else. So when we call our web service with both inc to be 2 and inc to be 4, make these two requests at the same time, it's going to run get and set. And for inc equals 2, for that one request, get is going to run before set. It must do, right? We wrote the code in a particular order. It must execute in that order. And for inc equals 4, the same thing is going to happen. Get is going to run before set. So usually when we write code, we have this sequential order in mind. But in actual fact, when we have concurrency, when we have these two requests that are happening at the same time, there's no ordering relation between them, right? My get for inc is 2 and get for inc is 4 can happen in any order. I've not described what order. So in fact, if we just have these two tasks, get and set, and two requests that are happening at the same time, we have 4 orders. There are 4 possible combinations of things that could happen. And this is known as non-determinism. There are going to be 4 orders, and we don't know which one is going to happen. So when the system runs, when I have my web service and it's running, and I issue these 2 requests, one of these possible sequences is going to happen. But I don't know which one until it actually runs. So this non-determinism makes things very, very difficult to actually work with, right? We can't predict the possible outcomes of our system. We can't test it, right? I mean, okay, here there are 4, but imagine when I have a more complex system, a more complex example, how am I going to test all possible cases of things that can happen? So concurrency bugs, they can only actually happen when we're actually running our system. Thankfully, there are some techniques that we can use to help us identify concurrency bugs. And when we're actually tracking a bug, when we're trying to diagnose what's happening, there are certain methods we can use. So one of them is thinking about our shared mutable data. So when you think about your code, I want you to try and do something. Split it up, mentally at least, into data and functions. So you have data, which are a load of values, and you have your functions, which are operating on that data. And then take a look at your data in a bit more detail, and try and find the bits of that data that are changing. That's what we call mutable. Now, in our case, the thing that was changing was our count. Now, once you've identified that mutable data, then try and identify which parts of that mutable data are shared among your different concurrent executions. So in this case, our count is accessed and modified, right, by any of our requests that come in. So our count is shared mutable data. Now we'll speak about how we deal with this in a sec, but for the moment, just identify it. So go through your code and have a look, try and identify all those pieces. Now, shared mutable data is really, really hard to manage. So the biggest tip for writing concurrent code is actually just to avoid it, as much as you can. And some languages are better than this, than others. In Rust, for instance, you have to explicitly declare whenever you're mutating anything. So it's actually quite good for helping you identify these parts and also encouraging you not to do it. In Scala, you have a lot of different things that you can use for creating immutable data, stuff that doesn't change. You have case classes, for example, vals. And in some languages, like Erlang and other actor systems, you can't actually share mutable data at all. It prevents you from doing so, and so you can't end up with some of these bugs. You do end up with others. So the second thing that you need to do, once you've identified all your shared mutable data, is identify any I/O that you're doing. So when I think about I/O, one way of thinking about it is that you're querying a database, you're reading a file, or you're printing something. Another way is thinking about all the things that you can observe. Imagine if you were looking at your system, your program from the outside, what would you see it doing? Would you see it making requests, reading from the disk? Now, if you do that, you identify all your I/O operations and all your shared mutable data. You end up splitting your code into two, if you like, the part that actually does that mutation and I/O operations, and the part that doesn't. And there's a particular term for this in functional programming. It's splitting your code up into side effects and things which are pure. Now let's try and do that here for our example, and then let's see how it can help. Okay, so first of all, I have this call to get that gets my count. Do we think that that's either getting or setting any mutable data? Yeah? Yeah, it is. Cool. So it's something we need to watch for. The next line here, we're printing what the count is. That's not doing any mutation, but it is doing a bit of I/O. Now, most of the time, when you're looking at code, you might think, oh, it's just a print line, it doesn't matter. But we'll see. We'll see if it does. Right, finally, we've got another line. I'm going to call this calc next. It's the thing that computes the next value. Is this getting or setting any mutable data? No, this one isn't. So we can skip that. Now next, we have this call to set, and that is setting some data, mutable data. And finally, we have another print. I'm going to label these get, print before, calc next, set, and print after, and that's just so that we can start talking about them in a bit more of an abstract sense. Okay, so I have these four things, and I know that they must happen in sequence. I've identified all the bits which are mutable, or touching mutable data, and all the bits which are doing I/O. And I identified that this calc next one, that was something that was pure, wasn't doing either of the other things. So I can actually safely ignore it. So when I'm considering the different orders of events that can happen when I'm looking for a concurrency bug, I can ignore all the pure stuff, and I only need to think about these other parts. So for this particular bug, the only things that I need to look at are get, print before, set, and print after. So I have these two requests, one with inc is 2 and inc 4. And now I know my operations, right? I know my tasks that I need to look at, which are going to affect my behavior. And then, this is the hard part, in your head, you need to go and you need to interleave these. So this is a possible sequence, which can result in our final state. Now remember that at the end, what we saw, printed out anyway, was that the count was 5, even though we expected it to be 7, but the state was 3. So in this case, both of the gets happen, one after another, and actually the order of that doesn't matter. Both of the prints happen as well. Our set, where our increase was 4, happens first, and so our count is 5. Then our set, where our increase was 2, happens next, but it still read the previous count of 1, right? So it actually sets that to 3. And then finally, we have our prints, right? We print after first that the count is 3, and then we print that the count is 5. And notice that those prints don't need to happen in the order of the sets, right? So the only thing that I know about this, you see, is that for all of the green operations, there's a particular sequence. And for all of the blue operations, there's a particular sequence. But I don't know anything about the order in which they're going to be interleaved. Now, this is one of the reasons why debugging concurrency bugs is very hard, because you assume sometimes that your logs are actually a reflection of what's actually happening in your system, right? But they can't be, they're I/O. So here are some tips for reasoning about this. First of all, avoid shared mutable data, but you can't always avoid it, right? In order to actually do any work, you do need to have some. And secondly, identify your side effects. Now that leads you, at least quite far along the way, to functional programming. It just so happens that in functional programming, you program largely with pure functions, and pure functions don't actually affect anything in concurrency, right? You can execute pure functions in any order. It's only the I/O operations and the mutable state that you actually care about. So by leaning towards pure functional programming, you make it a lot easier to debug these systems. So I said that we were going to talk a little bit also about the solution. So let's go back and have a look at this. Now, one of the mistakes I've made in writing it like this, right, one of the assumptions that I've made which was wrong, is that I've assumed that get and set are going to happen sequentially and also immediately. I'm almost assuming that get and set are one block, whereas in fact I need to describe them as two blocks. Now there are various solutions for this. One is atomicity, so maybe you might want something like an atomic integer. But actually a better solution is to take all of this shared state, all of the stuff you've identified, and put it in a separate data store. And that is because as soon as you start to think about scaling your system, as soon as you start to have two web services running, you can no longer share state between them if that state is purely inside them, right? You need to use some external data store to store that state. And then actually, your operations which mutate turn into I/O operations anyway, because you're querying this database. Okay, so we've talked a bit about functional programming and about how it can help us reason about systems. If you do want to adopt functional programming, then Scala is a great language for it, I will say. It does have lots of tools to help you there. But even if not, you can apply these techniques in any language, right? It's a mental exercise. Okay, now let's have a little bit of a look at the systems beneath our application, the things that are required for anything to actually run concurrently. Okay, now we've said that concurrency is about doing multiple things at the same time, and we've now defined what that means. That means that we have multiple sequences which are being executed in any order. But realistically, there is a limit to the number of things that a computer can do. And that's governed by their physical processes. Okay, I'm making huge simplifications here, by the way. There are many, many complexities, and this is just a basic model that you can use to try and understand some of them. So if you imagine that I have two processors, in a very simplified sense, that means that my computer can only do two things at once. If I want it to do 100 things at once, I need to have something in the middle of my application and the processors that actually decides how those 100 things are going to get run. And that is known as a scheduler. Now your app, when you run it, is probably going to be packaged with some libraries. It's probably going to be running on the JVM, and maybe that might be running on Linux, and that ultimately is going to be running on your processor. This might be the stack you're using, but it might be different as well, right? You might not have Linux, you might have a different operating system. You might not be using any libraries. You might not be on the JVM at all. So everyone's stacks look very different, and so the schedulers that they have are also different. Now, in general though, whenever we have m tasks, in this case 100, and we want to map those onto n things, in this case processors, we do what's known as m-to-n threading. Now it's entirely up to the scheduler as to how this mapping occurs. If we think about the ideal scheduler that we have, we would want it to interleave our tasks, but we wouldn't want it to split them up too much, right? So we would want it to interleave these threads of execution, but keep large chunks of them together. And that's because there's a lot of shared context between one and the other. And swapping out that shared context can be quite expensive. So let's say that you had an application before Java 21, and you decided to write it on the JVM. You decided not to use any libraries. You have thread pools, though. The scheduler that you would be using is the Linux one, assuming this is your stack. So the way that you give these sequences of tasks to the scheduler is by creating threads. Let's say that you had 100 tasks. You could create 100 threads. Now, the Linux scheduler would take those threads, and due to its nature, it tries to make things fair. It is designed really such that every process that's running on it, every thread that's running on it, can have an equal share of the processing. It does obviously prioritize a few. But as a result of the nature of Java applications, unfortunately what ends up happening is that we have a lot of switching between these threads. And so our threads get chopped up much, much more than we actually would like. Now, this is a huge oversimplification. I would love to talk to you a little bit more about why it does this. And the takeaway here is not that the OS scheduler is bad. It's excellent. But it's just not suited to the things that we usually want to do when we're writing web servers. Now, unfortunately, not all of us think about schedulers, right, when we write applications. And if you don't know which scheduler you're using, you might just be using the one that was on Linux. And so you would have quite poor performance, and you wouldn't really know why. But thankfully, Java 21 comes with its own scheduler. And you can use it by enabling virtual threads. So the JVM scheduler, which has virtual threads, works by taking all of those virtual threads, mapping your tasks to them, and then mapping those virtual threads down to OS threads or platform threads in a better way. And it hands those platform threads then directly to the processor, or rather to the Linux kernel, which schedules them on the processor in a more efficient manner. So what you end up with is work done in a much better way than otherwise. Of course, you could build really scalable concurrent applications prior to Java 21, right? And for that, you would use an async framework. So you would use some libraries, which you would package up with your Java application, which would contain a scheduler. Now, let's say that you were in Scala and you were using the type-level ecosystem. That comes with a scheduler. So that scheduler would be responsible for mapping your tasks down to operating system threads. Now, it does something that's very similar to the one that's packaged with Java 21. It takes your tasks, let's say you have 100, and it runs them on something that's called a fiber, which is pretty much a virtual thread. And then it hands that to the Linux operating system in terms of using a thread pool. And then that goes and schedules things on the CPU. Now, there are differences, by the way, in this scheduler and the one that's on the JVM. And quite often when you're picking between async frameworks, you'll have to decide which scheduler you prefer. Now, you might ask the question then, well, which is the best one, right? You might think that there is actually one answer. But when you're considering the stack of technologies that you use, I think it's important not just to consider the actual tech, but also to consider how they're maintained, how they evolved, and how healthy the ecosystem is. It's quite unfortunate, but usually when we're thinking about applications and we're writing applications, there are so many of us And there aren't actually many people who are writing libraries, or working on the JVM, or working on Linux. But sometimes the tools that are there for those people. They're there for those people to maintain their ecosystems in a better way. We'll talk a little bit more about how this ties into concurrency when we have a look at async programming. Okay, so we've had a look at the systems that are beneath us. And the key takeaway here is don't use the OS scheduler, not because it's bad, but because there are better ones. There are ones that are more suited to your server. You could use virtual threads. If you're just running on the JVM, you have no libraries, maybe that's a good option for you. But also, in the type level ecosystem, there's an excellent scheduler. It's not inside the Cats Effect library. Okay, so we've talked a little bit about reasoning, about how we identify concurrency bugs, and how we can design a system on paper such that we will try and get as few bugs as possible and make it as easy to reason about them. We've also talked a little bit about performance, basic performance, by looking at the systems that we're built on. But actually, you need a lot more than that in order to design a system at scale. You need to be able to represent quite complex control flow. And that's a little bit of a fuzzy concept. So let me give you a bit more of a concrete example. Let's say that I have a web service, and as part of one of my endpoints, I do a couple of things. I query this other Inc endpoint, but I also make another query to a database. So I have two things that I want to do at once. Now imagine that that database is a little bit flaky. I probably want to retry that query a few times, and I might even want to retry with something like an exponential backoff. And since this is a web service, I'm going to be responding to requests, I probably want to time this whole thing out. Let's say I want to have a timeout of something like 30 seconds. I need to now define all of this logic, and some of it can be quite complex, but ideally I would define it in lots of small building blocks that I would be able to put together. And this, in functional programming, is known as composition. In many spaces, it's known as composition, and it's just the idea of trying to build things up, put things together from smaller blocks in a way that that big thing still makes sense. Now, if we think about the things that we need, our units of composition, when we're doing any kind of concurrent tasks, we can identify a few. Well, the most basic is sequencing, right? If I have one thing that happens after another, that happens after another, I need to be able to somehow define that in my code. Now, in normal non-concurrent programming, that's just a series of instructions. So in Scala, if you're using something like the type level ecosystem, the way that you do this is using a for comprehension here. So it looks very similar to a sequence of instructions, but in fact, what you're actually doing is sequencing these tasks, these blocks. If you're using virtual threads in Java, what you would probably see as a sequence would in fact just be something that looked exactly like your normal code. There's another thing that we need to do if we're doing any form of concurrency, and that's to join things together. So if you imagine that I have two tasks that I'm running, and I'm running them concurrently, I'll want to be able to at least define that somehow, that I want them to run concurrently. So if you're in Scala and you're using the type level stack, there's a function for that. It's called partupled, which makes sense in its context. It means take a pair of things and then run those in parallel. Okay, so we can sequence stuff, and we can join things. You can join things in Java, by the way, using thread.join. But there's something else that I defined, which is actually rather complicated to write, and that's retry. So here's a signature for what a retry function might look like in Java. Let's say you're using completable futures, which are another thing that you can use to build these async programs. This function is actually quite hard to write. Does anyone think that they can write it? We're not sure. OK. So I'll leave that as an exercise to you. Try and write a retry, and try and write a retry using something like a completable future. In fact, you won't be able to. And the reason is this. This future that we have represents something which is already running. It represents a program which is running and will finish at some point in time. Maybe it already has finished. But because it's already running, I can't really retry it. How do I retry something which is already executing? And this is a big problem. It's a big problem because on a larger scale of composition, not just retries, it makes it really hard for me to try and define these building blocks that fit together. So in the Scala ecosystem, in Cats Effect, and the type level stack, there is a way of writing retry using their block. So their block is not a feature, it's called an IO. And the way that you retry with IO is that you just say that if there's an error, I'll do my IO again. The only reason that you can do this, though, is because this task here, this thing that's an IO, is not actually similar to a future. A future is a running task, whereas this IO is actually just an expression of a task. It represents a program that has not yet been run. And because I have a program that has not yet been run, I can refer to it again. So let's say that this task did something like print out hello to the console, and there was some error. When I retried, in this case, it would execute again, and it would print again. Now what that means is that I can actually compose things. So I can compose this retry. I can write it, but I can also compose it with all of my other operations. And it means that I can write some other operations too. I can, for instance, timeout. It's not possible, not really, to time out a running computation. But it is possible to take an expression, which is not yet running, and describe that you want to time it out. If you think about it, it's a bit like using a builder instead of using an actual future. So by treating our tasks, these blocks, instead of treating them as actually futures or as threads, if we start treating them as programs, that is to say expressions which are yet to be evaluated, then we end up with something which is composable. So you'll see this done not just in the Scala ecosystem, but also in Rust as well. So the Rust feature is also a computation that hasn't yet been performed. That means that you can actually compose it in this way. You can write functions like retry. But unfortunately, for all the other things that came before, you can't. So you can't do that for features in Java. You can't do that for features in Scala as well. And virtual threads, while they're a really good replacement for the Java feature, also don't have this property. So that means that it's really, really hard to write these composable building blocks for them. So you might wonder, right? This retry, okay, it's difficult, but that's not what I do, right? If you're an application developer, you don't write a retry function, do you? You will go and you will search online, and you'll try and find a library that does it for you. But the thing is that someone else actually needs to write that library. And someone else needs to write it in a way that is going to fit into your code and fit into everybody else's code. So this is why composition is important. It's not actually so important for the applications, right, on the application level, but it's really important for the library ecosystem. It means that you can have this really rich ecosystem with lots and lots of different tools for you to go and use. Okay, so we have a bit of a recipe then for writing concurrent programs and writing systems at scale. First of all is reasoning, right? You can all do this no matter what you're coding in. You can all take these tools to reason, and you can reason about your systems on paper. You need to look for shared state, try your best not to have it, and try and identify these side effects, these I/O operations, and mutable state. And lean towards functional programming. It will help you. We've looked at this big tower of tech systems that our app is based on. We've seen that schedulers are very important. So go and have a look. If you don't know, try and have a look and see what scheduler you're using. And once you've picked the best scheduler, then look for an ecosystem which has a really composable model. Make sure that whatever building block you're using to describe your tasks, that you can put it together, you can compose it. And with that, you'll get a really rich ecosystem. It will be an ecosystem that will not only be rich, it will actually be very easy to maintain as well. And it will mean that it will be very easy to reason about your code because the model that you have on paper matches the model that you have in your code very well. So if you take anything away from this talk, I hope it is that you feel like you yourself can build concurrent systems, and you can build them at scale as well. There is no magic, right? There is no secret recipe to it. It is just these tricks. If you want to learn more, please have a look at the type-level ecosystem, and in particular Cat's Effect, which is the library for asynchronous programming. There's also a reasonable amount of literature on how it's built as well. If you want to go and take a look at any other videos, any other resources, there are a few here for you. So I really like Daniel Spiewak. He's one of the people who contributes a lot to this ecosystem and has built a lot of it, and he has some great ideas. And so you can see his talk on effect systems, which are a bit of a fancy way of describing asynchronous programming, and also on threads at scale, which goes into a lot more detail actually about how schedulers work. If you want something that's a little bit closer to Java, maybe you came here and you expected to see a lot of synchronized and volatile. There's quite a nice talk called The 7 Deadly Sins of Concurrent Programming. If you do go and watch that, try and use the lessons that you've learned here in that talk as well. So try and take this as a view and see what you can learn. There are some talks which I think are going to be quite interesting as well, just later in this conference. One of those is What's Looming in Spring, which I'm pretty sure is definitely going to be about virtual threads. And another thing is 6 things we learned implementing Rockstar on Quarkus. If you want to find me, I have a newsletter, very recent. But I will hopefully blog about some of these things, and I am also writing a very small book on functional stream processing, which is very related to concurrency. You can email me as well, and find me on LinkedIn. I have a few repositories on GitHub and some other talks on GitHub as well. And then if you want to chat, I'm also on the Scala Discord, and you can reach out and talk to me about Scala. Or you can come in person. I organize the London Scala Users Group, and we have meetups each month. Right. Well, thank you very much. Questions?
Hello. So about the schedulers, do you have like a big performance loss to be able to, like when you're using like an application scheduler, because you are actually sorting the task that you want to do and overriding the schedule that the processor will do, that the processor is normally optimized for different type of instructions to be able to order and so. So is there a big loss trying to optimize, not optimize, but like set the proper order in the scheduler in your application?
No, no. So that's not quite the model of the way that things work. So it's not as though you're overriding the operating system scheduler. You're just giving it a different view. From the point of view of the Linux kernel, right, everything is a process, right? It has a thread, and things are just executed on that thread. It doesn't care what things. So if you have a scheduler above that, then all you're doing is that you're taking these blocks, if you like, of tasks, and you're putting them together in a chain, and just handing those instructions over to the Linux scheduler. So it's not as though the Linux operating system feels like it's seeing a different view or is being overridden at all, right? It's just that you're handing a different program to it.
If you give a chain, you are telling that it has to be executed in that order without other processes taking over?
Okay, the Linux scheduler, it will always override if it wants to, right? So it will time slice however it wants to.
Then you are never safe.
Sorry?
Then you are never safe. You are not thread safe from modifying the same variable because it will slice it and then maybe put together different instructions from different tasks modifying the same.
So I think thread safety on that level is a slightly different thing. But in terms of, so you were talking about optimizations though, were you not? Or?
Well, the processor will try to make optimizations, right?
Yes.
So then it will maybe cut from another thread because it will pause this thread because it's waiting for an I/O that is slower. Then another thread will jump in, and then you have the same problem of multiple writes or multiple reads.
Yeah.
Same value.
So blocking I/O is another really, really important thing. I would love to discuss that as well. But to explain that, in general, when you're using these asynchronous frameworks, and also when you're using virtual threads, another thing that you will do is that you will be using a different strategy for doing that blocking I/O. So you won't actually block, you'll be non-blocking. You'll do something like use epoll, as opposed to actually using a blocking read call. In fact, what virtual threads do, it's quite interesting, is that they'll kind of override, so instead of actually making that blocking read, they will be using something like epoll. That makes sense? I'm not sure if that actually answers your question. But
And now for a different question.
Yeah.
Perhaps it was just so comprehensive.
Oh, cool. Great. Well,
Okay.
thank you very much.